Well, good afternoon, everybody. Welcome to the MQ Thursday afternoon seminar series. Today's speaker is Dave Nolan. Dave got his bachelor's in physics from Harvard College in 1990 and a PhD in the Earth and Planetary Sciences at Harvard in 1996 under Brian Farrell. His interest is in vortex dynamics in general. He said anything that rotates except for the Earth. He's had postdoc positions in UC Berkeley, Colorado State, Princeton. He's been a frequent visitor here. And then he became a faculty member of the University of Miami in 2002, and he's unfortunately been serving as the chair of the department, I guess, since...
Year and a half.
A year and a half, and how much longer do you have to go?
It's not clear. Not clear. Until I find a way out of it, I think is how it works.
Yeah. Anyway, he works a lot with Rich and George, and they're doing work on tornadoes and on tropical cyclones together because they're both vortices. So I'll leave it to you.
All right. Thank you, Maurice. And I want to thank everyone for coming, and thank Rich and George for having me and my postdoc, Nathan, over there as guests. Actually, I just got a text from Dan Stern. It says, "Is it worth it for me to watch the live webcast of your NCAR seminar?" And so I wrote back, if you haven't read the paper, then yes. So, all right. Maybe he's actually watching the live broadcast right now. So, okay. So this is work that I've been doing on and off for a long time with my colleagues from HRD across the street from our school, Eric Yulhorn and Jun Tang. And I'm going to start off today's talk with some words of inspiration, basically why we're doing this stuff. And this is some poetry, if you will, from someone I consider a personal hero. And the words are, "I can't tell you what it really is, I can only tell you what it feels like." Now, does anyone recognize that text? No? I'll give you another line. "And right now there's a steel knife in my windpipe." Anyone? Now, these are words written by Eminem. Rich, you know who Eminem is? So this is kind of basically the inspiration I have for this work. Here's an outline of the talk. The topic is, how well do we estimate tropical cyclone intensity? Even in the best situation, how well do we really know what's happening in a hurricane? All right. So I'm going to tell you about in-situ observations and the concept of undersampling. But in fact, we're always undersampling. I'll show you observations from a simulated tropical cyclone. We'll talk about winds from perfect observing system, winds in suboptimal systems. I'll talk about introducing the effects of errors and also gusts. And then I'll go back to an issue regarding the current in situ framework, and give some conclusions at the end. Okay, so how well do we estimate tropical cyclone intensity? So today, the vast majority of estimates, which are used to make the very famous best track data set of tropical cyclone intensity, are made by satellite images. And they're just images produced by satellites. Right, so this is kind of a standard Dvorak satellite image in this kind of funny black and white grayscale. And it can be used either for a subjective analysis, which means by a person, by hand, or an objective analysis, which people have developed more recently. And the subjective analysis is pretty interesting. There's actually a step. I've seen this because I sort of went through it with them step by step, like live, at the Hurricane Center, where they actually take a piece of plastic and put it on the screen to count like how many eighths around or tenths. Is it tenths really? And basically around the center that there's convection. Okay. Now, if you want something a little more objective, you can take the AMSU technique. There's one of Julie's papers, which basically the AMSU satellite can see temperature anomalies in the atmosphere from microwave radiation, and that can give you an estimate of the warm core. It really only gives you the estimate of the upper level warm core, and from that you can back out from thermal wind balance a vortex structure, which is actually broader and weaker than it should be, and we know that, so we can sort of correct. But that correction is based on the best track. Okay. So some people have thought about this before. John Naff et al. Compared Dvorak satellite technique estimates to best track estimates when aircraft observation, so just satellite versus satellite plus aircraft. And so they estimated the satellite-only root mean square errors are 10 to 12 knots. Torn and Snyder attempted to estimate the uncertainty of the best track by comparing satellite estimates to each other, different satellite estimates at the same time, and also to best track values, again, when aircraft reconnaissance was present or not. And they estimated a lower bound for root mean square uncertainty of 8 knots. And then in a very different study, Chris Lancy and James Franklin tried to estimate the errors, and they did it by polling the NHC forecasters, asking them, what do you think the error is? I mean, that may sound kind of silly, but actually it's a nice contrast to the more analytical technique. So anyway, and what did they got? They got an estimated error of 8 to 10 knots. Okay, what's underlying all of these is a very high confidence in the information provided by in situ data, either by aircraft or surface observations. What it's saying is that, in the case where a hurricane is right over a tower or a plane went right through the center of that hurricane, okay, that's like the gold standard. That's really good. Now, there's another sort of separate issue, which is how we define intensity. Right? Because the intensity definition is a little weird. Right, so the official definition of the intensity of a depression or a storm or hurricane is this quote, which James Franklin is very, very particular about: the highest 1-minute average at 10 meters associated with a weather system, and I really don't know what that means, but anyway, at a particular point in time. We're still arguing over what that means. But I think you might not be surprised. Observations, damage analyses, and numerous anecdotal experiences, like I personally have had, and some people in the room might have had, to show that the wind field is highly variable in space and time. So there's that like helicopter image, and like here's one house blown away, and here's another house which is not, and so on and so on. So it's reasonable to ask, even with very ideally located observations, what are the chances of observing that maximum wind, right? Or to put it mathematically, what is the average underestimate or negative bias for in situ observations? And I think it's really important that we do that. Because if we don't, we're going to get stabbed in the neck. Oh, is that what Eminem would say? But so let's go forward. So we did some of this already. So in a paper by Eric Uhlhorn and myself, we addressed this question regarding flight data from airplanes. And the data from the airplane is from the step frequency microwave radiometer. And that is, if you don't know, that's a device on the bottom of the plane which detects microwave radiation coming up from the ocean. And the faster the wind blows, the rougher the ocean surface gets. And that changes the spectrum of microwave radiation coming up from the ocean. And you can actually back that out into an estimate of the wind speed at the surface from your plane flying at 10,000 feet. It's pretty amazing. So what we did is we took a simulation of a hurricane, a really good simulation of Hurricane Isabel that I'd done before. And Eric flew hypothetical flight tracks through it where the plane was looking down and getting this surface wind basically every second. And this is called a figure 4, and this is 2 rotated figure 4s. These are the standard flight patterns. And we basically generated hundreds of these so we could develop statistics. And this is, to summarize that whole study in one figure, this is the result. The red line here is the simulated maximum 1-minute wind speed anywhere in the hurricane, and that's every hour. And then this blue curve is the running 6-hour mean. And we say running 6-hour mean because that's what the Hurricane Center does. When they say at 0Z the wind speed is 100 knots, they mean the average peak wind over the last 6 hours was 100 knots. So it might have been 110 at one point, it might have been 97 at one point, it's going around. It's the average over 6 hours. So to be fair, you take the red curve, you average for 6 hours, you get the blue curve. The green is what we found from the simulated flights. And each point here is the average over 8 flights starting from different points on the compass. So you basically do 8 flights, you average over that and you get the center. These are the 2 standard deviation estimates. And what you see is you miss, right? You almost never observe the maximum wind, even if you do a perfect figure 4 with perfect instruments, perfect measurements in a hurricane. And in fact, on average, the underestimate is 7.8% for a very symmetric major hurricane. Now, the Hurricane Center loved this because it basically completely agreed with what they've been doing for years, which is basically bumping up 5 knots. So SFMR sees 100, it's probably 105. SFMR sees 70, it's probably 75. And that's about what 8% correlates too. So they were very happy with that result. So what we're going to do now is we're going to try to take this to another level and talk about in situ surface observation, because those are the real gold standard for hurricane intensity. If you get, say for example, a tower or an instrument or a buoy that survives a direct hit from the eye wall, that's the best possible estimate of intensity you could get. So we're going to place, instead of a plane, we're going to place simulated anemometers in the path of a very high quality hurricane simulation. What I call high quality is what we call the Hurricane Nature Run. I actually gave a talk here on that about 3 years ago, and you can read all about it in this paper in James. And it's basically just a very high resolution, computationally expensive physics simulation of a hurricane in a big domain, nested down to 1 kilometer resolution, run for 13 days, with the model output saved every 16 minutes for that whole 13 days. So this is just basically this is the storm, goes across the Atlantic. This is a simulated satellite image. This is a simulated reflectivity. Looks very nice. And we did extensive validation of this simulation, compared observations, and you can read about that in the James paper if you like. Okay, so this is the life of the Hurricane Nature Run. There's a genesis phase, and then it moves across the Atlantic and it recurves. And as I said, all fields from the 1 kilometer grid were saved every 6 minutes for that 13-day period. But during 4 separate stages, we also saved the surface winds from the 1 kilometer grid, just the surface fields, every 10 seconds for 6 hours. So thanks to the WRF developers in the room, because WRF has that option. You can save some fields, different frequencies than others. And that's actually what I've overlapped here, the red and the purple and the green and the black here. Those are basically the periods with the 10-second output. So if you have 10-second output, that first actually allows you to compute a 1-minute average, right? You can take the last 6 actual outputs. That gives you a 1-minute average. And as I'll show you in a moment, there's no loss at all due to time interpolation. That's basically faster than the fields evolve significantly. So, okay. So here's what the wind field looks like. This is a snapshot of surface wind speed in what I call the mature stage, right? So the hurricane has intensified, expanded, it's become a great big monster over the central Atlantic. And these little blacks here, like that's where you get your peak winds, just a little bit above 60 meters per second. And that's 1-minute wind. Actually, these are probably instantaneous winds, because these are images. Anyway, and so if I animate in time, you can see how isolated those peak winds are, right? They're just those little black spots, and they tend to form over here and move around here and then disappear. Whoops, like that. So this is every 1 minute. I'm showing every 1 minute here. Okay, so this looks pretty cool, right? But we have no idea if that's what a hurricane wind field actually looks like. Because we have no way of measuring the whole surface wind field in 1 instant, and certainly not with 1 kilometer or even a few kilometer accuracy. The only thing we can compare to that's even close is point observations from towers. So fortunately, some people have put towers out in the ocean and also on land and have been hit by hurricanes. And those towers have been configured, have been especially set up to record data very frequently. So let's see how well our simulated hurricane winds compare to tower data, right? So we're going to compare to the 10 hertz, that's 10 times per second, tower data by Ping Zhu, this paper, and this paper by Jun Zhang, 2011. So the blue curve here, this is from the model, that's simulated winds at a fixed point. Not the maximum anywhere, fixed point simulated winds. And these gray curves in the back here, that's tower data, which is just chosen to be about the same speed. And well, you can see, of course, it's not even close. The tower data is extremely noisy, gusty. But remember, our metric is the 1-minute average. So if we take the 1-minute average of both of these, we get this comparison, which is clearly the tower data is still noisier, but it's not too bad. We're not that far off with our model output. Now, of course, another way to look at it is with power spectra. So these blue curves are the power spectra for 4 different towers. There were 4 towers this data set came from. And here's the 5 minus 5/3 curve we all love. And these gray curves are spectra from many different points, simulated towers in the path of the hurricane. And the red line is the average, and you can see, well, in here we're doing pretty well. Not surprisingly, there's a gap, right? This is the gap between models and reality.
Dave?
Yes, George.
Where were the observed towers located? Were they on?
They were on land. They were on coastlines, on land, and generally, like a few kilometers from shore. And these were generally done with onshore winds. So you're probably thinking, well, maybe they would be even rougher than they should have been. Absolutely true, right? So, yes, Peter.
Just as a thought experiment, suppose you took the blue stuff and you filtered it to the same resolution as to which you modeled. That's really the right comparison.
No, but I can't do that because it's point data. The model is spatial data.
Using Taylor's hypothesis, I'm sure you could craft a transfer function that did something to the blue curve that got closer to what that.
But all I can do to the blue curve is smooth in time. And it's not hard to say if I just smooth this in time, I'm going to get this, right? Anyway, well, listen, we're going to talk more about this later. So, no, you should interrupt me if you're inspired. Anyway, but to your point, right? So basically, if you care about, this is the 10-minute. Basically, we're 10-minute, the 10-minute wind frequency, and so this is 10 minutes here, I should say. So if you care about 10-minute winds, actually, we're doing really well with our hurricane simulation. But for 1-minute winds, we're not cutting it. Okay. So let's get back to this issue of undersampling. Suppose we place in the path of our storm an array of fixed towers that report perfect observations of wind speed and pressure. So I'm imagining someone has put out in the middle of the ocean this array of 17 by 17 towers spaced 1.1 degrees apart. And I've gotten really lucky and my hurricane has gone directly across the array. Now, you can look at this and say, wow, well, surely one of these towers is going to observe the peak 1-minute wind speed, right? It's a direct hit. So here's a plot. The black curve here is the actual maximum 1-minute wind every 10 seconds. All right. Now, these curves all in here are from the middle column of that array I just showed you. Right? So these are numbers 1, 3, 5, 7, and so on up to number 17. Right? And so here they're all over the place, but you can see they're all well below the actual maximum. In fact, many of them, including ones which you think would do really well, like say number 11, which is in the right side of the storm, they get close a few times, but they're always short a few meters per second. And in fact, if you use all of those arrays, all 289 towers, you get the pink line. It's the maximum over every tower. And even that comes up short every now and then. Well, it's always short, and it's often quite a bit short. So, let's imagine a framework of observing systems, right? And to inspire this framework, we'll think about what we want to measure. We want to know over a 6-hour period, that's the Hurricane Center's averaging period, these different variables. V1, I'll call it V1 peak. That's the peak 1-minute wind that occurs anywhere, but as a function of time. So V1 peak is a function of time. That's the black curve I just showed you. V1 max peak is the maximum of that over the period. So that's the peak of the black curve, the highest value of that black curve I just showed you. And V1 mean peak is the average of the value over the period. So that's the average of this black line here, the average of that black line. And that's similar to what NHC means when they say best track. They mean the average peak wind over the 6-hour period. So to make our optimal observing system, we do a test. First, we do our 17 by 17 array, and we get the highest value of wind we observed at 63.73 meters per second. Now, if I double the number of points, quadruple, double the resolution, it goes up to 66.3 meters per second. And if I double that again, I actually get the same number, 66.3 meters per second. So it basically converges. So if I had an array of 65 by 65 towers separated by 0.025 degrees or 2.5 kilometers over the ocean, and a hurricane went directly over it, then I would know exactly what the peak wind speed was during that 6-hour period. Okay. So, now let's talk about suboptimal observing systems. So the 65 by 65 array is our optimal observing system. A typical suboptimal observing system is one. One instrument gets a direct hit from a hurricane, survives, reports. So let's imagine this hurricane hits a single fixed instrument, and let's just even give the benefit of the doubt, that instrument gives you perfect winds. So on average, how much is that single perfect anemometer going to underestimate the peak intensity? So we're going to do a test. We're going to randomly choose an anemometer that would be ideally located. Basically, what I mean is someone at the Hurricane Center would say, wow, that's a great observation. That's got to be it. Okay? So that's going to be on the right side of the storm, and it's going to experience the radius of maximum winds. Basically, direct hit from the core. Okay, we record V1 max peak for that anemometer. Repeat 2,000 times, and take an average. Okay, but before I show you the results, this just to illustrate it better. So this figure here is called a wind swath. This is not a snapshot. This is the peak wind observed by every point over the 6-hour period. Okay, and you see it's got a lot of structure, right? For example, here's a point that gets 55 meters per second, and right next to it is a point that only gets, say, 43 meters per second. This is the storm center. These X's are examples of these ideal anemometers. Right side of the storm, inside the RMW. So these are just randomly selected ones. And then this cross here, that's actually the actual peak. There it is, 66.3 meters per second. That's where it occurs. So that's the thing we're chasing. And these are the places we're trying to find it. Okay, so we do basically one anemometer, pick a random location, get the max wind, repeat. Take the average over 2,000 times. We get 57.5 meters per second, right? So the truth, remember, is 66.3. So one direct hit, we're missing 6 meters per second. Not too bad, but that's still basically 10% short. All right, well, suppose we were unbelievably lucky, right? And we had 2 perfect observations, a ship and a buoy, right? Well, if we do that, if we basically take 2 anemometers, repeat 2,000 times, 2 different anemometers, by the way, 2 different locations, then our max wind is 59.5 meters per second, right? So we've gone up from 57 to 59.5. So you can imagine where this is going. We can just keep increasing the number of anemometers. And basically the values go up. So what's on this curve? Well, here's V1 max peak, right? The average of that over the 6-hour period is V1 mean peak, and that's this dash curve. So if you're chasing V1 max peak, you're coming up way short on average, right? You're basically, whatever, 10, 15% short. As you increase the number of anemometers, you go up, but you're not going to get close. You're going to be, even with a lot of anemometers, which is very unrealistic, you're not going to get close. Now back to our 1 anemometer, the standard deviation, this is 2 standard deviations, right? So that 1 anemometer, maybe you reported this, but it could report this, or it could report this. But these really low values are not out of the realm of possibility. But there's one piece of really good news, and this is just luck, I think. We can talk more about it later. But the average value predicted by 1 or 2 anemometers, the maximum over that 6-hour period, turns out to be very close to the time average of the actual maximum. Right? That's the best track value. See, these are very close. So as long as we know what we're comparing, we actually can get pretty close with a great observation to the best track value, what the Hurricane Center would say is the strength of that hurricane. So if I take this figure and I recast it as percentages, all right, so this is the underestimate in percentage. If you're comparing to the peak, you're way under. You're under by 12%. But if you're comparing to the mean peak, the best track value, you're only under a few percent. And in fact, so in this range, 1 to 3 anemometers, just like you're almost right on. So let's imagine this. Suppose my model was perfect and my methods were perfect, and this curve was perfect, right? Then what I could do, if I know the bias, I could subtract that, and that would leave only random errors. And that's what this curve is. This is the residual random error, assuming the bias is perfect. So if everything I did here was right, and my residual error, my bias was perfect, this is the limit. Basically starts out around 5% for one anemometer, and it asymptotes to about 2.5%. I'll say 3%. That is the actual absolute limit of measuring hurricane intensity. Okay. Well, there's other measures of hurricane intensity. There's the 10-minute wind. This is a curve. This is values and percentages for the 10-minute wind. And for the same storm, you can see that all the values are basically reduced. But all the percentages are basically about the same. You know, as long as you know what you're comparing to. It's a little bit, so basically here's the peak wind. Here's the observed wind from 1 or 2 or 3 or 4 anemometers. It's well short of the peak wind, but it's close to the best track wind. Basically the percentages are all about the same. And this is for surface pressure. And for surface pressure, the errors are very small. If you have if you have an anemometer very close to the center of the storm, you're going to get a surface pressure that's very close. And so see, these are millibars, 935, 936, and 937. Just a few millibars. In this case, for the winds, the criterion for a great anemometer is right side of the storm inside the RMW. For a pressure observation, the criterion is observing less than 10 knots. I just made that up, but you could choose something different. But you know, the Hurricane Center, if they wanted a pressure and they saw a buoy that reported less than 10 knots, they'd be like, wow, that's the pressure of the storm. And in that case, they would be really close. All right, well, this case is really favorable because the wind field is nice and fat, right, in the mature stage. But hurricanes are not always in the mature symmetric stage. This is the stage I call after rapid intensification. So this hurricane has just shot up to Category 4 intensity, and for a moment, before there's an eye wall replacement cycle, it looks like this. So you can see it's much smaller. That's, you know, same, drawn to scale. And these are the winds, these are the winds moving around. I guess I only got a few images here, right? So basically now, if we look at the wind swath, which is here, the peak wind is actually about the same, 63 meters per second, like I said before. But it barely happens. It happens in this one tiny little location because the core of the storm is so small. This is the wind swath. And you can see this wind swath is even more chaotic than the previous one because the wind field is so small. But we do the same procedure. We pick anemometers on the right side of the storm inside the RMW. And then we take samples 2,000 times, calculate the average, and so on. Now what's interesting here is that for the small hurricane, our underestimates compared to the peak intensity are even larger because that peak intensity only happens for such a brief location and time. But the 6-hour averaging actually helps you out, right? Because you're going to take this period, you're averaging 6 over this whole period, and that takes this line way down to here. So again, 1 or 2 anemometers giving you perfect observations in a hurricane will actually get you close to an equivalent best track intensity. And that's shown here in the percentages. Again, it's basically a few percent. Random error is the best you could do. This is 1 minute, and that's 10 minutes, which is, you know, just a little less. There are other phases of the storm. This is what I call the sheared tropical storm stage. Now this one was a little more challenging because the wind field is very disorganized, right? The center of the storm is here. You've got this convective band over here, which is basically giving you high winds over here, and then this sort of other shadow wind region over here. And the storm is actually moving southwest at this time. So this is the wind swath. And in this case, I had to change the procedure. I couldn't identify an RMW or a right or left side of the storm. So I just said, okay, any surface wind more than 18 meters per second, I'll say would have been a good one. And then I basically sample those, run it through. And we get some very similar results as before. They basically very, actually the percentage, what happens is the percentages actually get larger because the average wind is so low. This is all around 30 meters per second. So when you look at the percentages, even 1 or 2 anemometers are actually underestimating the intensity of this storm by about 10%. Okay, so now let's take a step forward and try to make this framework a little more realistic. And I'm going to add errors, right? So we go back through the whole procedure, but to every 1 minute observation, I'm going to add a 5% measurement error. Now, that's actually a very large error. But for the moment, let's add a 5% measurement error. Right? So here's the result I showed you before. So if I take every observation and I add a 5% random error, the maximum observed winds go up because you're not averaging, you're picking the maximum. So what happens is these blue curves all just shift upward, right? And that gives you this result here. So it doesn't really change very much. But when you add random errors to the winds, actually your reported winds go up because you're picking the maximum. But the V1 max peak, these values, the truth, are not really changing. So basically all you're doing is you're reducing negative biases. The fact that there are errors actually reduces your undersampling, which is kind of a, I know it's even more, it's an awkward result, but it's because you're picking the higher value. So, as I was saying, so observational errors cause biases to be shifted towards more positive values, right? So this is the percentages, and you can see the percentages have all gone up. Now we're missing the best track by less than 1%. But 5% error is actually very large. If you have a good anemometer on a tower and it survives, and basically in the 1 minute wind it measures is very, very accurate. It's probably more like 1%. And so this figure here shows the same results, but as a function of measurement error. And what happens is 0 is no measurement error, and 1 or 2% is more realistic error. So what I'm showing you up here is here, but in reality, everything's over here. So really, observational errors from well-calibrated instruments have almost no effect. Now, the bigger question is, could we make the simulated winds more like observed winds, right? Because we know the observed winds have gustiness that we just can't simulate. So here's my observed power spectrum I showed before. What we did is, first of all, we got this formula for an observed power spectrum from this book by Kymall and Finnegan. You know that book, Peter? Anyway, so, yes, is that a joke? I didn't know until Jeff Kepper told me about it. So.
We don't talk about hurricanes at all in that book.
Anyway, so we got this formula, and we fit it to this curve here. Okay. But then I thought, okay, but I don't want the low frequency power from that curve. I want the high frequency power. So I took that formula and I made up this crazy exponential function to wipe out the low frequency power, right? So that basically turns the blue curve into this pink curve. All right. And then I generate random time series with that power, right? So I'm generating a random time series, which is basically the sum over the wave numbers. Here's your power spectrum. Here's the frequency shifts. And this theta here is a random number between 0 and 2 pi. And then we take those fluctuations, those randomly generated fluctuations, and we normalize them according to the current intensity, right? So I take my random fluctuation, and this power spectrum was built around winds with a mean value of 32.5 meters per second. So if the simulated wind is above that, I bump up the power spectrum. If the simulated wind is below that, I reduce it. So that's what this factor is here. And conveniently, I can take the 10-minute wind, which is varying in time. So the enhanced wind is the simulated wind plus the random noise scaled to the current simulated wind. So then I take those winds and I run them back through the power spectrum, and I get this red curve. So previously I had the green curve, now I have the red curve, and voila. I've filled the spectral gap. Okay, so here's some examples. This black curve hidden back here, that's an example of the simulated wind at a fixed point, right? So you can basically imagine, being approached by the eye wall, right? And the storm's getting stronger and stronger, and boom, you're getting into the eye wall of the storm. This red, that's just the fluctuations only. So it's basically this curve added to that black curve. But remember, we always convert to 1 minute wind. So we take these, convert to 1 minute averages, and then we get this here. And so it's not actually so different, but you can definitely see, there's your 1 minute averaged fluctuations. So what does that do? So here's my original result I showed you. Here's the peak wind, here's the average wind, here's the average observed wind by 1 anemometer. When you add these fluctuations, you're increasing the reported winds, but you're also increasing the truth. So they both go up. So these black curves go up here. Now somewhere in the storm, you actually, instead of a 66 meter per second wind, you get a 72 meter per second wind. The mean goes up, but everything goes up. And so basically nothing changes. So our attempts to add gustiness to the wind, it did, it basically, I'd like to say it gives us confidence in some of these results because everything shifts up together. But to be honest, to be fair, what did we really do, right? It was a neat trick, and I'm glad it didn't, disprove our results. But this is what we really did. I took this wind swath, and by adding random fluctuations, I made this wind swath. Now, this doesn't look so realistic anymore, right? All I did was add random noise to my swath. So obviously, if I had this at whatever 100 meter, 10 meter resolution, it wouldn't really look like that. So maybe it's a good result, maybe not. You have to understand how you made that result. Okay, so now I'm going to go back to the issue about in situ observations as they're done today. Okay, now previously I told you about this result here where we calculated that two repeated figure 4s through a hurricane will on average underestimate the actual intensity by about 8%. Now this is a snapshot from the simulation we used to do that study. That was from a previous simulation. And this is from a couple of papers that we published in 2009. Looks pretty good, not as good as the Nature run. But another thing is when we did that study, we only had hourly output of the three-dimensional fields. So in fact, when we were flying that plane through the storm, we were interpolating the winds in time and space from hourly data. Not optimal. But, all right, we got a new model. We got 6-minute output. What happens if we do it again, right? So the Hurricane Nature run is 1 kilometer resolution, 60 levels, and data every 6 minutes. What happens? Well, we repeated the process, and actually now we did it over the whole lifetime of the storm. What we did before was only for a steady state Category 4 hurricane. So this is over the whole lifetime, and we actually get a much bigger underestimate, right? So now I have to go tell James Franklin to bump up all the hurricanes from the last 30 years. By 5 knots. So we're still studying this. I mean, maybe we're doing something wrong, or maybe undersampling is even worse than we expect. But where the undersampling is terrible is during this rapid intensification phase, right? The figure 4 says it's at 37 knots, and in reality, it's at like 50 knots. Sorry, 50 meters per second, right? That's a huge gap. You're always behind the curve of the hurricane. Now, I also want to just talk a little bit about pressure estimates, right? Frequently, the best pressure estimates come from dropsods, right? So that's an instrument that's on a little parachute that's dropped out of the plane, falls down through the storm. And when they're flying through the eye, where it's calm, they try to release a dropsonde near the center so that it will fall down and actually hit the ocean in the center of the storm. And so the last pressure observation that they get before it hits the water is considered the surface pressure, the best estimate. But, they don't always make a direct hit on the center. In fact, they usually don't. Often, they don't get the center. And the way they know that they don't get the center is there's a wind report also, right? So a simple correction is made, and it's illustrated in this nice little summary here from the Hurricane Center about Tropical Storm Cristobal. Let's see. Earlier reconnaissance data indicated maximum 850 millibar flight level winds of 61 knots. In the southeast quadrant, where SFMR, that's the thing from the plane, winds of near 50 knots were reported. Therefore, the initial intensity has been increased to 50 knots. A NOAA aircraft reported a central pressure of 996, but the dropsonde reported 33 knot surface winds. That's pretty high, right? So the central pressure is estimated to be 993, right? So they have a rule of thumb at the Hurricane Center of a millibar per 10 knots. If the dropsonde is reporting 20 knots when it hits the water, you subtract 2 millibars, and that's your intensity, right? Well, does anyone know if that's true or not? I don't think anyone knows, really. But we can figure it out for ourselves. So here is a simulated, but I like to think very realistic, surface pressure field, right? So this is contoured. Oh yeah, there we are. It says right there. Every 1 millibar, right? So look, there's a lot of structure in here. It's pretty cool. Right, so depending on where your dropsonde lands, you're going to get these plus or minus a few millibar reports. And so what we do is we take data like we take these fields and we just sample them randomly and we make a scatter plot of pressure versus wind. And it looks like this. So this is the pressure difference between the reported pressure and the true minimum, as a function of the surface wind speed. And so what you see, I've drawn on here, is the NHC rule of thumb. Well, it turns out it's pretty good, right? It's right down the middle of the scatter plot. So I don't know really how they could do much better. But what's more interesting is over here, right? Because look, suppose they had like a perfect hit. Wow, 0 wind, great. That's actually off, because the storm is moving. So the wind center and the pressure center are not in the same place. So actually, if they get 0 knots, they should actually add a millibar, right? And actually, the perfect surface pressures are observed with these basically 10 to 15 knot, 10 to 15 meter per, 10 to 15 knot wind speeds. So anyway, this is something else that we're going to flesh out and try to come up with some more results on. Okay. So to summarize, the peak winds reported by 1 or 2 anemometers that experience a direct hit from the strong side of an eye wall will, on average, come very close to the average peak wind over a 6-hour interval. This is very weird, because this is totally apples and oranges, right? One's a point measurement, one's anywhere, one's the max over the period, and one is the average of the value anywhere over the period. And yet somehow they're kind of, and maybe there's like some underlying mathematical lemma or something finding in there that could basically make me show that's true, but I haven't figured it out yet. So you can think about that. Anyway, now if that's true, in that situation, under perfect conditions, the limiting accuracy for estimating hurricane intensity, that's what I call the bias-corrected mean absolute error. That's between 3 and 5%. Let's just say 5%. If you add errors to the observed winds, that actually increases the average reported winds, and that reduces the negative biases. But for realistic observing errors, it's a very small effect. If we go back and try to add fluctuations, gusts, to the simulated winds to make them more realistic, that actually just ends up not changing any of the results significantly. But we have to concede that the true variability of the 1-minute wind speeds are probably not yet resolved, clearly. And so, in fact, the negative biases and the bias-corrected mean absolute errors may still actually be slightly larger than that. So, if any of my students were here, they'd probably get mad because I've forbidden my students from showing this figure because it's so cliche. But I'm going to show it. Basically, this is the one where everybody tells you that you should give them money to do hurricane research, right? So, and what it shows is that the error of the 24-hour forecast. In case anyone in this room, has anyone in this room not seen this figure before? Anyone not seen? Really, Morris? Come on. Don't you go to conferences? Okay, so this is so I'll say what's on it. This is the official intensity error and trend for Atlantic hurricanes, right? So basically, the 72-hour error forecast errors have been steadily decreasing. Good job, America. 48 hours, but look, 24 hours, it's like flat, and it's actually coming back up again here. It's going to be back up over here. This is a little anomaly. And this is actually because they cheat. I'll explain to you. If you ask me later, I'll tell you why they cheat. Anyway, but this is so from our friends Lancey and Franklin, Torn and Snyder, and Naff et al. This is actually the limit of the current verification capability. We couldn't even know if we were doing better than this. And the purple line here is if things were truly, truly perfect, if the observations were all perfect and all my calculations were right and the bias was exactly known, this is where we could get to. So, all right. Any questions? Oh, thank you.
Time for questions, comments?
Oh man, it went fast.
So your most recent simulation with the much higher time resolution produced what appeared to be much larger uncertainty in the
actual... for the SFMR.
Right. So. And so it was kind of going by fast, but I want to know, so do you think this number is going to end up closer to what was the original numbers you showed at the beginning of your talk?
8%.
8, 10, 12, whatever. It looks like they're kind of all converging on a number that's somewhere around 10%.
Okay. It's a little different. I mean, so this is here, this is basically simulated SFMR data. Remember, that's basically a plane flying a figure 4. So really, that hits the eye wall 1, 2, 3, 4 times, and 2 of those times probably don't matter, right? So basically, I think if we keep doing this, this number is going to keep getting bigger. And because if we go to higher and higher resolution, more realistic hurricanes, I think this number will keep getting bigger. And it's a little shocking. What the simulation I did before was 1 kilometer, you know, I don't know, but that was WRF 2.2 with, you know, WSM5, and now I'm using WRF 3.4 and WSM6 and more vertical levels. And so, you know, I think as we resolve more, I mean, this actually may get, you know, will get worse. So I think we're actually just kind of getting a feel for what I don't see where this undersampling is going to converge. I guess that's how I'll answer your question. I don't see where we're converging. I think we're going to figure out it's worse than we think before we improve again.
But I guess the point is, if we're undersampling, but the uncertainty.
Oh, the uncertainty, right. Yeah, that's different. If you know the bias, then you can get to the uncertainty.
Okay, so
Right.
Is your uncertainty bigger in this estimate? Probably. Maybe you haven't done that, but do you
I have
think
not
it's-
done that. I mean, I think it's about the. I mean, if you just assumed it was this, right? It's about the same, right? But if you don't know your bias, you don't. Yeah. So. Any other questions?
Rich, you look like you're pondering. Wait a second.
I'm going to explain that to you later, Rich, because you really don't want to know. Peter, do you want to go back to that issue about? I think, you know, maybe let me rephrase your question for you, Peter. The question is this: if I have this wind field and I have this tower data, how can I use this tower data to improve this wind field? Right?
You need a relationship between space and time.
Right.
Okay. The simplest one is Taylor's hypothesis.
Right. But I have to say, Taylor didn't live in a hurricane, right? And I mean, I'm not trying. I know I'm making a joke, but in all seriousness,
I was trying to do a quick calculation where
Right.
The grid's a kilometer. Let's say the surface wind is 30
50,
meters
60,
a second.
no, more like 40, 50, let's say 50 meters per
Okay,
second.
so if you take 50 divided by 1,000, that's like 0.5 hertz, something like that?
It's
That's-
50 by 1,000. No, it's 20.
That's
It's
that
20
would be the-
seconds.
That's the most you can get from the time resolution of the model. Lambda f equals u. Okay?
Right. Well, I mean, another way to see that is here's from actual model output, like these blue curves. Right. This is actual model output every 10 seconds. Right. So basically, yeah, the time of variability is like this, which is about like 100 seconds. So.
I'd have to sit carefully more.
Yeah.
It's going to be something like
Right,
that.
right.
Okay, so you're never. The other thing, I was just kind of curious if you have actually made a PDF of the measured winds,
PDF of the measured
of
wind.
the actual wind speed,
Right.
whether it actually looks Gaussian.
Oh
or
yeah,
it's-
you know, I wish
or
I.
whether it's nicely skewed, and because you're adding random
Right.
fluctuations to your.
Okay, so in other words, you're basically asking what's the PDF here, right? Like that? I mean, of just any observations or yeah.
The real observations.
Oh, I
It's
see.
like old-fashioned PDF of the wind.
Oh, old-fashioned PDF of the wind. Would it be skewed? I can't say. It might be a little skewed.
It's just that the turbulence isn't Gaussian. That's the point.
But what about turbulence in a forced dissipative layer, right? I mean, if you know,
It's just not.
but how far from Gaussian is it?
Depends on.
If I make a PDF of this thing, it's going to look by the eye. It'll be pretty close to Gaussian, and there'll be a little kurtosis and so on, but it's pretty close.
See, if it was truly Gaussian, you wouldn't have any flux. I mean, it's.
Right. That's fair. Yeah, fair point.
I'm just wondering, since you're talking about the wind bias, so then if you look at the momentum equation, that's the the pressure gradient, momentum flux transport. So do you have any idea which one is more the suspect on the bias? And I know from observation you have a tower, but it's overland. Maybe it's hard to compare the momentum transport compare with the modeled drag
Right.
things like that. So, but I'm just curious about the suspect behind this.
Well, let's see. But it's not clear to me what you're asking me. So,
What causes the bias, the wind speed bias?
what causes the bias is the big bias has to do purely with undersampling. You've got this big complicated wind field, and you're just picking points, and the field is so highly variable in space that your chance of catching that, getting a good representation of the maximum is just really small. It's really, sort of back to Peter's issue. If I were simulating a large expanse of a turbulent boundary layer, but homogeneous, right, we could probably do kind of what you're proposing. But it's the combined effect of, yes, it's turbulent, and it's incredibly variable in space. There's this structure, right? There's no wind here, there's little wind here, there's strong winds here, and embedded in the strong winds are areas of high winds that are moving. So I would say it's the spatial inhomogeneity that is really the cause of the undersampling.
One more question.
I'm trying to think of how to relate this to the work by George and Rotuno when they looked at their 62.5 meter grid spacing run. And it's been a couple years since I looked at that paper probably, so my recollection may be wrong, but in that I thought that they kind of had the peak winds kind of peaked out around 1 kilometer, and then as they resolved further down, they got more of the gust structure, but the average of that was not quite as much. Is that correct? And I'm just wondering if that's the case, if a 1 kilometer nature run might kind of actually maximize the estimate of the undersampling, but it might be by
I see, because I'm like overestimating peak winds.
Yeah, I'm just curious about that.
That's a reasonable question.
And if so, would it be warranted to repeat this experiment at a really high resolution for a small?
Well, I mean, doing everything again high resolution is always warranted. But no, I think what you're basically, so in their study, what they found especially that when they just compared basically the predicted maximum 1 minute winds and a series of simulations with increasing resolution, the 1 minute maximum kind of peaked somewhere, like around 1 kilometer, 500 meter resolution, then actually went down a little bit. I think it was only a little bit it went down. It's kind of, right? When it got up like 8,
If you want my opinion on the answer to the question,
I would like.
I would take a 1 kilometer resolution run over a 100 meter resolution run. I'd say if you don't go down to 10 meters or so, you're wasting your time.
So 1 kilometer.
You say that for everything that you study.
So okay, but so basically, I mean, the point is this one has a PBL scheme, right? This is all that stuff is parameterized and parameterized pretty well, as people found. So
Okay,
anyway, Quentin?
one more question.
I was curious about, so you were showing the spectra of tower data and things like that, but realistically what we're normally dealing with is this SFMR data at a best estimate. But the SFMR is trying to measure surface roughness roughly. What's the response rate of that in terms of spectra? I don't even know if it's 1 hertz.
Oh, I see what you're saying. Well, it's way less than that. I mean, you see, again, it's like the plane's flying at 100 meters per second, and it's sampling, I think it is around 1 hertz, I think. The SFMR, it might be 10 hertz, something like that. But every sample is, quite a distance. So basically, at every point, the microwave, you're just getting at that instant the microwave field coming up from below, and there's a response time to that, right? Basically, so if the wind increases, how long does it take the sea state to catch up? That's probably in the order of minutes. So that's just another complication. But I want to emphasize that this whole study is done in the context of perfect observations. What I'm getting at is what are the limits, even if SFMR were perfect and all that response was instantaneous and perfect and correlated to 1 minute wind, that's the limitations I'm getting after.
But in terms of trying to give it tone and error, though, you have to also consider the error of the instrument in terms of sampling.
Right, and you have to basically you take this approach and go back and add errors of the instruments and so on. I did a little bit of that, but we haven't done that for SFMR.
And with that comment, we will call this to a close and thank
Thank you,
Dave.
everyone.